Good morning. Welcome to the session on Integrative-AI. My name is Sean Andrist. I'm a researcher here at Microsoft Research. And I'm very excited to introduce to you three different talks in this session that all center around this very difficult problem of creating real end-to-end intelligent systems that can operate in the open world, that can leverage and coordinate multiple components, speech, language, dialogue, planning, learning, and sort of tie it all together. So, technology has made a lot of progress recently in these individual wedges, but it is still incredibly difficult to sort of tie these things together and actually make a real system, which I'm sure many of you have run into. So today we're going to hear talks that introduce some recent advances in this, some recent systems that are integrative, that tie multiple components together. We're going to learn about some core challenges, how to do troubleshooting and blame assignment. And then at the end, we're going to learn about some tools and platforms that can actually make this all possible. So our first speaker is Louis-Philippe Morency. Louis-Philippe is an assistant professor in the Language Technology Institute at Carnegie Mellon. He also leads the Multimodal Communication and Machine Learning Laboratory. And today he's going to talk about core challenges in multimodal integrative AI systems, focusing on machine learning and particularly deep learning. So please join me in welcoming LP.
Thank you. Thank you. Thank you, everyone. My name is Louis-Philippe, became in the US LP, too long for this. I will be talking about multimodal machine learning, or if it was a longer title or more catchy, it will be probably deep learning for multimodal system. It's an exciting time to be working on AI, given all the advances that happen on these integrative AI systems, virtual human robots, HoloLens, and some of the living room or ubiquitous computing. And so I was lucky enough to, early in my career, working on one of these projects. 43 people working together. A lot of them are in this room. And one thing you learn about this is the challenge of integration. And so I will present one of this, which you may have seen, some of you, but let me introduce Ellie, one of these systems.
Hi, I'm Ellie. Thanks for coming in today. I was created to talk to people in a safe and secure environment. I'm not a therapist, but I'm here to learn about people and would love to learn about you. I'll ask a few questions to get us started. And please feel free to tell me anything. Your answers are totally confidential. Are you okay with this?
Yes.
So, how are you doing today?
I'm doing well.
That's good. Where are you from originally?
I'm from Los Angeles.
Oh, I'm from LA myself.
Great. One of the core challenges when you build this technology is to understand and interact, communicate with humans. So how do humans communicate? The 3V of communication: verbal. Every time you choose to speak, you often decide on specific words. The words or the phrasing is important. The pragmatics is even more important. Pragmatics means word in the context of a social interaction. But there's also the second V, vocal. Every word, sometimes I call it the 50 Shades of Yeah, and I stole that, in fact, from my previous postdoc, Stefan. 50 Shades of Yeah, because every word yeah, 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 yeah. Each of them has a slightly different meaning, and so that's really important for a computer to understand. And since my background was in computer vision, I'd put the big emphasis on the third V, visual. Gestures, arm gesture, but one of the important things, the first that I often look is gaze. You also have facial expression. Facial expression is important, not just the basic emotion, but all these emotions like confusion and surprise as well. So this is the challenge, one of the big challenges when we build integrative AI is how can we create computers to recognize communicative cues? And so the challenge that I will talk about today is how do we integrate verbal, visual, and vocal information to infer something about the user, something about their emotion, their social cues, or if it's in a clinical setting, something about maybe depression, anxiety, or PTSD. This is something that has been studied a lot. And there's a lot of really interesting work on multimodal. Multimodal, by the way, started, if you look early on, in the 1970s. Really interesting works. Someone knows about the McGurk effect? McGurk effect? Okay, so this is a wonderful effect that if you use the same audio tract, exactly, fa, 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 and change the visual track, shows a different mouth shape. Human hear ba, 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 simply by the change of the visual. And that excited everybody in multimodal. And this is one of the aspects that started all the work on audiovisual audiovisual speech recognition. This computational era came with a lot of interesting work in multimedia and also in psychology. There was the landmark work with David McNeil on language and gesture. But suddenly in 2000, we started looking at interaction, human interaction. And what happened in 2010 is definitely the deep learning era. Today, I will emphasize on that last piece of this because this is probably what most of you are here to talk about is deep learning. How can we not talk about deep learning? But I want to tell you that there's been a lot of work on multimodal from which this work is building upon. When we look at deep multimodal machine learning, taking this verbal, vocal, and visual and fusing them together, there are 5 challenges that are important in these cases. The first one is representation, alignment, fusion, translation, and co-learning. I'm talking about them, and I will give you more details in a second. This is, if you have a chance, this is a full survey on this topic. There's more than 253 references. But the more important thing is if you are to study a field like multimodal, you need a taxonomy. So that we can interact together and talk about the same thing. And that's what I will introduce first in the first part of this talk. And then I will give you real-world example of recent progress on this topic. So the first one is probably one of the most interesting one is representation. How can we learn to represent and summarize multimodal data in a way that exploits complementarity and redundancy? The first kind of approach, if you look at the literature these days, and probably the first one you thought about when we think about representation, is joint representation. Joint representation means that you're bringing together the data from one modality and another, bringing them jointly together. And let me show this visually. What will a joint representation for human communication looks like? It is a representation where if I say the word, I like it. Or if you see my joyful smiley face, or you hear the joyful tone, you would like these 3 very different behaviors to all come to a similar place in that joint representation. Similarly, for more anger or some tense voice, you would like this, or even for surprise, you would like to learn this joint representation. And this sounded for me like science fiction. But thankfully, there's really smart people who push on this, and this is, in fact, there is a possibility that this is possible. And that came from the work, early work in the 2009-2010, looking at joint representation. There's some early work back in Stanford, really great work from Roslin. But here's the one example that really blew my mind. And it is doing vector arithmetic in that field, in that space. And what do I mean by this? And what do we do? I learned a joint space where images can be represented and word can be represented in that space. And what will we do? We'll do arithmetic. I take my image, I encode it, and then I take the word blue, and I subtract to the image. I take the word red, I add it, And then I take the coding, and then I start sampling from there. And what do you start getting when you sample? Red cars. And the same way you can do with yellow cars, or you can do with day and night. This was really, for me, eye-opening. This was a moment where you see there is a way of bringing language and vision together. And these were separate fields for a long time. I was probably one of the few in 2008 that went both to ACL and CVPR at the same time. I'm quite sure of that because they were overlapping in time exactly at the same week. But now these days we see a lot more researchers doing between the two. But this is joint representation. But if you ask me where I believe this line of research is going now, is coordinated representation. Coordinated representation does not force to have this one joint space, but says, hey, I will have a space for my language representation. I have a space for my visual representation, but I will coordinate between them. What does this coordination mean? It has different flavor, but one of them is the recent work here at the University of Washington and TTI on deep CCA is a great example of coordinated. What is the challenge when you learn independently language representation and visual representation? One of the challenges, if I ask you the first dimension of my language representation, how does it relate to my first dimension of visual representation? If you learn them separately, there's no coordination. The CCA allows you to coordinate the dimension of that representation. It does it in such a way that the first dimension will be the one where there's the most correlation with your data. Most correlation with your data does not mean the exact same thing. It just means that we have you find the basis, the space basis or the space axis where the correlation is the highest. And then you repeat it over for every dimension in such a way that they are orthogonal to each other. This is a great example, I believe, to have space that are coordinated, but at the same time, they are separate but coordinated at the same time. This is the first challenge, representation. The second challenge is alignment. I have all of this data, and I want to identify the direct relations between elements from two or more modalities. What does it mean? One of the examples is explicit alignment. And there's some really great work early on with Sri and Carlos and others who are doing alignment where you want to align one modality explicitly with another modality, where you want to align your gestures with your language or your verbal with your voice at the same time. Or there's another type of alignment which is implicit alignment. And implicit alignment is the most popular these days. Most popular these days because what it is you have a task in mind, maybe a fusion or you have a translation in mind, but as an intermediate state, as an intermediate step, you will do this latent process of alignment. So it's an intermediate, but your objective function does not have alignment directly. So here's an example of implicit alignment. I give you this task of doing image captioning. You have an image and you want to learn the caption. Internally, in your mind, you've done implicit alignment. You realize that the dog is related to this object, that the tennis ball is part of this, the murky water is the rest of the image. You've done that implicitly as part of the task. And now these days, there's beautiful algorithm doing some of it for us. One of them, also beautifully named, Attention Model. Attention Model is an example of a process where I want to predict from an image, try to predict my caption. But as I'm doing this, I will decide where an image should I look at. And I do this over and over in such a way so that eventually when I create the caption, a woman is throwing a frisbee in a park, you can see the attention moving over time. So this is an example of implicit alignment. This is the second core challenge. The core challenge is what everybody thought of multimodal before, fusion. Fusion is the task to join information from two or more modalities to perform a prediction task. And the perform a prediction task is the most important. We are closer to the objective function. A representation, you're closer to the input at that point. So the most well-known approach for multimodal are early and late fusion. Early, you concatenate your input, and then you have agnostically a model that learns the prediction task, or late fusion, where you explicitly do the task in one modality and then the other, and then have a fusion later on in later stage. But this is the older way to look at fusion. Now these days, there's a lot more work on deep learning doing fusion. The problem and the solution with deep learning is that the boundary between representation and fusion in a deep network architecture is often really fuzzy. Where is it that I'm doing the classification task and where is it that I'm doing the representation is a gray zone. But there are approaches like kernel-based approaches that are clearly fusion-based approach. Multi-kernel learning is an example where each modality will have its own kernel, its own similarity metric, and then that will help with the fusion. Or graphical models. I know, why are you still talking about graphical model? I strongly believe in graphical models. I believe that this is a great way when it comes down to fusion or down to bringing the prediction task, that's often where the place graphical model will shine. This is the third challenge, fusion. The fourth one is translation. The process of changing data from one modality to another, where the translation relationship can often be open-ended or subjective. And there are two types of these. That's part of the taxonomy. One is example-based, where you have example and you use it as part of your model. Another name for this will be non-parametric and parametric. That will be another way to look at it, where you're learning this, but your model in itself has this data as part of the model, where in a parametric approach, you will learn a model that approximates your data and then use it during the translation. And I will take this from a great friend, Stacy Marcella, which collaborated with Stefan Scherer on this, where this is a translation problem. There's some folks here who worked on this problem, where I will take only the transcript and the audio of a movie and automatically generate the visual gesture. So everything you will see there are the visual gesture that are automatically generated. Early work on that was the beat system from Justin Cassel is another great example. So let's see this all in real time. Oh, that was a really short one. Okay.
You snotty little bastard.
Your Honor, I'd like to ask for a recess.
I'd like an answer to the question, Judge.
The court will wait for an answer.
If Lieutenant Kendrick gave an order that Santiago wasn't to be touched, then why did he have to be transferred? Colonel, Lieutenant Kendrick ordered the code red, didn't he? Because that's what you told Lieutenant Kendrick to do.
Object!
And when it went bad,
That'll be all,
you cut
Counsel.
these guys loose!
Your Honor!
You had
Counsel, I'll
Marcus
hold you
inside
in
a phony
contempt.
transfer!
Your Honor!
You doctored the logbook!
Damn it, Captain!
You coerced the doctor!
Consider yourself in contempt.
Colonel Jessup, did you order the code red?
You don't have to answer that question.
I'll answer the question. You want answers?
I think I'm entitled.
You want answers?
I want the truth!
You can't handle the truth.
And one of the biggest challenges in translation, what is it? What will it be? It's evaluation. How do you evaluate a good translation? And people in machine translation knows that it's a big challenge. And it is also challenging when you translate between modalities. That's one of the big challenges. And the last one is co-learning. This is the transfer of knowledge between modality, including the representation and predictive model. The idea is I have a task in one modality, and I will be using another modality to help the task in the first modality. The co-learning can be happening when you do have parallel data, where you exactly the same instance in both modality. Or more challenging is the weakly supervised approach, where you have data, but the supervision between it is more at the group level or at the cluster level. And often you have the hybrid version of that. So this is a summary. I mean, if you have too much time and you really want to fall asleep really quickly, there's a survey paper of 24 pages that gives you the full taxonomy of multimodal machine learning. This is available on archive at this point. I wanted to give you this first summary before giving you 3 examples, concrete recent progress in multimodal machine learning, making it more concrete and hopefully tools that you can use in your own research as you're building integrative AI system. One is about representation, the second is about alignment, and the third one is about fusion. But the first one is probably the most important, looking at representation. I have this verbal, vocal, and visual data represented as a text, image, and audio, and I would like to predict sentiment. Why do I pick sentiment? Anybody in NLP knows. In fact, they're probably tired of hearing about sentiment, but there's work on multimodal sentiment that is done through a video. And in this case, if I learn a joint representation, then my internal representation, HM, is a direct function of each of my representation from the text, image, and audio. This theory is great. If you have infinite amount of data, don't worry, learn from that. But in many cases, we don't have infinite amount of data, and you want to learn, but also put interesting knowledge into it. Let's look at sentiment as an example. Sentiment has 3 types of interaction: unimodal, bimodal, and trimodal. The unimodal interaction is the following. You have a unimodal cue. This movie is sick. It is still ambiguous. It could be sick, and now I'm adding the multimodal, so there's no way for me to do it without the multimodal. But this movie is fair, or a smile. These are cues that will show positive. It is ambiguous how strongly positive, but this is in itself a cue. And loud, whoops, oh, it comes automatically. Loud, I'm loud. That I've been told. But doesn't mean I'm always positive or always negative. Loud is an ambiguous one. This movie is sick, and then I have also a smile. Then, or a frown. This is the bimodal interaction. This is resolving the ambiguity that I previously had. But if I say this movie is sick, and I say it loudly, you're still ambiguous in what it is. But trimodal interaction are really interesting because this movie is sick with the same nonverbal will be really strong, while this movie is fair, which is a really strong verbal cue, will in fact does not change the interaction. So when we build representation, we need to take into consideration the unimodal, bimodal, and trimodal interaction. This is why we, instead of doing a simple joint representation, we will learn what's called a tensor fusion network. A tensor fusion network looks like a really simple equation until these are really important. These one are really important. Why are they important? Because they are the one who will automatically create for you the unimodal representation and the bimodal representation. And since we're in a world where everything is 3D or 4D, let's make a 3D version of that. Can extend it to 3 modalities. And the 3 modality has the unimodal representation in green, the bimodal representation, and the trimodal. So you have a representation that explicitly encodes trimodal interaction, bimodal interaction, and unimodal interaction, making it easier for the model to learn. And that's what we see in experiment on many different topics, but this one is for multimodal sentiment analysis. By using this representation, you get an improvement of a state-of-the-art very significant. And as a good teacher, a professor, you always go back to your student and say, hey, is it really that you need all of them, or is it just one modality that's much stronger? And yes, you need all 3, bimodal, unimodal, and trimodal to get the improvement. The second example I wanted to talk about is temporal attention. I'm talking a lot. Not everything I say is important. No, everything I say is important. So as a human, we're really good at attentive. Some cues, some evidence we pick, and a lot of things we ignore. We're really good at this. As you become more senior faculty, I learned that you're even better at selecting, like at doing at the right time, yes. So how can we have computers also learn what is important temporally? We suggested this new algorithm, which is an extension of existing approach where as you get the input observation over time, you will have a layer that looks at what is important in this video, takes this and learns some saliency score, and then eventually take this information in a recurrent attention gate unit. This attention gate is really interesting. It's a simple one but powerful one. Taking the hidden representation that I previously had, it will do two things. It will decide based on the inverse of the attention. So if I say, hey, this segment, don't attend to it. What does it mean? It means bypass. Bypass completely and forget that this ever happened. But the opposite is true. If the attention here is really strong, then I want to take into consideration that observation. That's a simple gate, but that is a simple gate that improves performance because automatically, by using that, you can automatically realize which part of a video is really important when you do classification. This is for event classification in this case, where you realize which field or which image are the most important for the task that I have in mind. And eventually, you will see the field again in a second. The last one I want to talk about is multimodal sequence of video. So if I do a sequence modeling with Lsdm, this is easy. We do it. We've done it. It works wonderfully on language. But for multimodal, what will be the way to do it? The multimodal way is to simply do some kind of early fusion where I just add the other modality in my Lsdm. But we want to do it in a multimodal way where information between modalities is coupled. What do I mean by coupling? I mean that we will create a multi-view Lsdm. What's in the multi-view Lsdm? The multi-view Lsdm takes as input, like a normal Lsdm, the previous hidden state and the observation at time t. But the magic here comes at the first stage where you look at what's important at what I just observed and do it in such a way that I keep a multiple memory cell. And here's something that I find really important. You remember how I told you joint representation, do it, but be careful, maybe coordinated is better? The same true for Lsdm. If you put everything in the same memory cell, then you force your algorithm to do all the hard work for you. So instead of that, we will have 3 memory cells, 1 for each modality, and then we will do the same input, forget, and output gate, but each of them will be multi-view. Multi-view is where the important aspect happen because there's different topology, and that's really cool. So let's play with it. What can we do with these different topology? Because what do we have as input of this module? Is if I want to know for modality 1, how do I represent modality 1? I definitely take the input from modality 1, and then I have the hidden state for modality 1, but I also have the hidden state from the other modality. So you can do is have 2 different design parameters, alpha and beta, that tells you how much do I trust my current view and how much do I trust other views. And then you can start playing with things. You can say, I only trust my current view. That's a view specific. Or I only trust the other views when it comes down to remember the temporal. Or I want to do fully connected, but the more interesting is the hybrid, where you look at a different weighting of the different modalities. So this is a quick version. The hybrid works really well on the children engagement because it takes into consideration the interaction between language, gesture, and voice, and learn that into a temporal aspect. So I appreciate your attention. The take-home message that I want to give you, the 5 core challenges in multimodal machine learning: representation, alignment, fusion, translation, and core learning. If you're really interested, please look at the survey. And I wanted also to give you 3 examples where you look at representation, temporal attention, and multi-view Lsdm. Thank you very much for your attention.
Okay, we have time for some questions. Please speak your question into the microphone. We have a mic runner right here. Right here.
Great talk. So there's kind of an implicit assumption when you're presenting that the different modalities are alignable, but some cases the meaning arises from a misalignment between the modalities in a sense. So sarcasm would say something positive in a negative way, or when I'm masking my anger with a smile, that conveys very different meaning than if all the modalities are aligned. So I'm just curious to what extent you have looked at, or people have looked at, where the meaning arises from the disconnect.
That's really interesting. So I will say there's more work to be done there. The part of the previous work that look at this problem is the people who look at implicit alignment. So I have a task which is looking at sarcasm, and as I do this task, I will model the misalignment implicitly, a latent variable. But the part that is important in your case is I need to do this implicit alignment condition on my task. And a lot of the current work, they will do the alignment more as a way to erase this misalignment and ignoring it. But in your case, you want to condition that misalignment to the task you have in mind so that you take that into consideration. And I've not seen as much work that condition it. There are a lot of work that will try to forget about the misalignment. For machine translation is an example where this misalignment, you in fact just want to handle it, but not take advantage of it. But I think this is something that to be done. There's some work in that direction, but there's more to be done, yeah. Great.
Any other questions? Okay.
You gave us examples of how deep learning is useful to you in many multimodal problems. Okay. No?
Yeah.
Okay, I'll repeat my question. So you gave us beautiful examples of how you're using deep learning for solving a number of multimodal problems. My question is where it doesn't work. Do you think it's going to fix all of your problems in multimodal systems? Or this is good for a particular set of problems and you're going to needing other approaches or hybrids or other things? Yeah,
and this is a very important question. I don't know if Yoshua is here. No, okay. But you will get different answers from different researchers. I will share my insight. I think of human communication, not I think, but a lot of work on human communication look at it as a loop. So perception, reasoning, and action. This is a really simplistic. And I think that deep learning is very good in the first part of perception. As long as you can get objective, reliable labels for your objects that you see, for the words you hear, it does very good at this. When it comes is uncertainty. It does not always handle uncertainty as well. Other frameworks, Bayesian frameworks, for example, handle uncertainty in a better manner. So you can imagine that when you get into the reasoning, this is where you need to be able to handle uncertainty. And because data is always limited in these cases, you probably also want to think about it from reasoning, but you want to be able to handle with limited amount of data. So I think this is where, at this point, you will see other approaches happening. And that's where you start seeing some interesting work. When you come down to the action, the same thing happens. If it is a clear action that you want to generate, you start seeing interesting work on generating a flower just from there. The problem there is open-ended. That's a problem that, and deep learning has a lot of problem in that, is when the problem is open-ended, how do you handle all the different aversion and how do you evaluate that? But for perception, I think this is great. Reasoning will need some help, and when it comes to generation, deep learning probably can handle it, but we need to handle how to evaluate it. And we need new objective function to know how to evaluate that. Yeah.
Okay, great. Let's thank our speaker once again.
Thank you.
Okay, and our second speaker in this session is Besmira Nushi. Bessa is the newest member of the Adaptive System and Interactions group at MSR. She just finished her PhD at ETH Zurich, and I think this is week 3 of her position here at Microsoft Research, so she is diving in head first. Her research is at the intersection of machine intelligence and human crowd intelligence, and today she's going to tell us a little bit about how to troubleshoot these systems. So go ahead, Bessa.
Thanks, John. So today I'm going to talk about our work on troubleshooting.
Oh, yeah.
You need to turn it on just 3 seconds. Yeah. Wait 3 seconds.
It's 3. Okay. So I'll talk about our work on troubleshooting integrative machine learning systems, and this is joint work together with AJ Kamar, Eric Horvitz, and Donald Kosman. So we are these days living and working in exciting times, and we are seeing many applications of AI being developed and applied in many problems, not only in academia but also in industry. And only in the last few years, we have seen multiple cases of successful AI applications in transportation or personal assistance or gaming and problem solving. Now, this is indeed very impressive and a great motivation for all of us. However, despite the recent developments, in the last few years, we have also seen a couple of events where the deployment of AI systems in the real world has caused unpleasant events for the end users. For instance, this is the case of a Google captioning app which tagged a human as a gorilla. Another example is the case of Tay, the Twitter bot that started making socially unpleasant conversations on the web in less than 24 hours. And I guess the bottom line for both these examples, and I guess for many more examples, is that intelligent systems still fail. And when they fail, the outcome may actually be disturbing for the end users, and it may cause the end users to lose trust in these systems. And this is the reason why we focused our work on troubleshooting machine learning systems, so that system designers can understand their systems better, and they can take multiple approaches in order to make them better. And this, of course, goes in the same line of thought on the concerns that Barbara raised this morning on her keynote, that once you understand the mistakes of your system better, and once you know more about the errors that the systems make, you can be able to improve the system in the future. So I'm not sure why this is automatic as well. Did you solve that?
The automatic?
Yeah.
This is not me.
Okay. In particular, we focused in troubleshooting integrative machine learning systems, or in other words, machine learning systems that are composed of components that are machine learned. These components communicate with each other. They exchange data input and output among each other. And of course, they provide a single output to the end user. And since these systems are not yet perfect and they sometimes make mistakes, there might be multiple ways on how to apply fixes on each of the components. And these fixes may be expensive. Now, the challenge that we are aiming to solve in this work is the following. Given the multiple possible fixes for each of the components in an integrative system, and the limited development time from the side of the system designers and engineers, we would like to know, or to give this information to the system designers, where should they invest the development effort in order to have the biggest impact. Now, of course, there has been previous work on troubleshooting. However, most of the work has been focused in troubleshooting physical devices or devices that have these hardware components. They do not have any uncertainty in the output data, and the physical components are clearly separate from each other. Now, when we started working on integrative machine learning systems and troubleshooting, we realized that troubleshooting machine learning systems presents many new challenges to face, mostly because the output of machine learning components has a lot of inherent uncertainty in the output data, which then creates complex interactions in the system architecture. So I'm going to illustrate what I mean by this by using our main case study in this work. Our main case study was an image captioning system, which takes an image as an input and it generates a textual description for this image. And this is a system that is running in the real world. It was also developed at Microsoft Research in 2015. It has 3 machine learning components. The first one is a visual detector. It sees the image and it generates a set of words as an output that are associated with a certain confidence score. Now, the second component, which is the language model, it takes this as an input, the list of words, and it generates a set of sentences that are plausible and could serve as final captions for this image. And finally, the caption re-ranker sees the image again. It computes similarity scores between the textual descriptions generated by the language model and the image, and it outputs one sentence as the final best caption. And in this case, it is a man flying through the air on a snowboard. Now, let us have a look from this system where the image captioning system has generated the wrong output. For this image, the system outputted the caption, "A blender sitting on top of a cake." And let us see what is the data that flows within the components and how can we analyze this data and what is going wrong here. Now, if we go back to the visual detector, we can see that the list of words that was generated by the visual detector has the word blender in there, which is wrong, but however, it has a very low confidence score with respect to the other words like teddy, cake, or bear. Then the language model has generated a set of sentences. The final best caption that was selected by the re-ranker is in this list, and it has also a low likelihood in terms of how suitable is this in terms of language. And finally, the caption re-ranker has many other alternatives, but however, it has chosen this one as the final best caption. Now, in this case, which of the components would you blame or would you fix in order to solve the problem? Would you blame the visual detector because it has detected a wrong word, although with a very low confidence score? Would you blame the language model because it has generated a sentence that does not make sense? Or would you blame the caption re-ranker because among all the other choices that it had from the language model, it has selected this one as the best one? Now, as you can see, the problem is challenging here, and the interactions are complex. And the first thing that we did when we started working on this was to actually characterize the problem of troubleshooting for the case of integrative machine learning systems. And we saw that these systems have 3 main characteristics that make the problem particularly challenging. Now, the first characteristic is that machine learning models and components, they usually have continuous quality measures, which means that their system state is not binary. And our question here is, in this quality continuum, where every component is partially failing, but also partially succeeding in performing its task, how can we quantify the effects of each component's quality into the final system quality? Second, many of these systems, because of bad architectural design or because of reusability and so on, they may exhibit a complex component entanglement, which means that the responsibilities between the components, they might be entangled and blurred. The boundaries between the components might be blurred. And our question here is, how do we disentangle the effects of component failures on the overall system? And finally, what we have seen with working with such systems is that actually improving one of the components does not necessarily guarantee you the improvement of the final system. And what we want to do with our methodology is to actually detect such cases of non-monotonic error propagation, where improving one of the components may deteriorate the quality of the final system. So based on this problem characterization, we developed a human-assisted troubleshooting methodology where we introduce people in the system execution. Here, people investigate on the output of each machine learning component via using predefined crowdsourcing tasks. So what they actually do is that they check the output of the machine learning component, they check whether there is an error in this output, and they fix this output. And after that, we are able to reintegrate the fixed output of the component back into the system execution. So as you can see, people here serve as a mechanism for generating simulated improved states of the components so that the system designer can see whether this improved state can actually make the system better and which of the components actually is going to make the system better. And notice that the human intervention at this step is actually crucial to the problem of troubleshooting, because only in this way we are able to simulate these improved states of the components and be able to integrate them back into the system without making significant development effort. So we collect all these traces about the system execution, the way how the system has failed, the fixes that have been applied on the failures, and how the system evaluation has changed after that. And this provides a rich set of data that is available to the designers. So except that, in our methodology, we can also execute a set of fixes in a single workflow. So a workflow is a set of fixes that has been applied one after the other in a single system execution. For example, in this case, we would be able to apply the fixes from the first component, and then only after these fixes have been applied, we apply other fixes on the third one. And so after applying a joint workflow execution, the system designers can see what is the joint impact of one or more fixes or one or more components at the same time. So what can one expect from such a troubleshooting methodology with respect to the problem characterization? Well, first of all, you could detect non-monotonic error by introducing fixes in one of the components and measuring the system quality before and after the fix and checking whether this impact is actually positive or not. Another way how you could use this methodology is to quantify the component impact by applying individual and isolated fixes on the components and then checking whether you can find any component that has where you should invest the most significant development effort. And finally, if the system designer suspects that two components are, for example, entangled and wants to test this, he or she could implement individual fixes in, for example, the first two components and then apply a joint fix and make the proper measurements afterwards. So let's go back to our case study and see how we applied this methodology in the image captioning system. For this system, we developed customized crowdsourcing tasks for each of the machine learning components. For example, for the visual detector, we asked people from the list of words to see whether they could add or remove objects that should be mentioned in the caption, or whether they could add or remove activities from the list. For the language model component, we asked people to flag and report sentences that were generated by the language model, but they probably had bad English, or they did not make sense in the real world. And finally, for the caption re-ranker, we asked people to check the top 10 best sentences generated by the caption re-ranker and to tell us whether there was actually a better sentence in this set that could have made it as the best caption. And what we see by collecting this data is a set of statistics and information that we could provide to the system designer. This is an example of applying a visual detector fix. Here the word kite is wrong, and after people could remove this with the crowdsourcing task and introduce the word umbrella, then the caption becomes from a blue and yellow kite to a blue umbrella in a field of flowers. And of course, the data that we collected is rich and it has a lot of information. Here I'm going to show a summary of the results that we had. In the y-axis, I show the percentage of cases where the caption that was generated by the system was considered as satisfactory from the crowdsourcing workers. And we can see that from the evaluation of this system, only in 57.8% of the cases, the caption was considered as satisfactory, which also gives you an idea of how the quality of the systems is at the moment and how far can we go. By applying individual fixes in each of the components, we can quantify their impact. For example, in this case, we can see that the caption re-ranker fixes are actually the most promising ones. And by applying all the fixes one after the other in a single workflow, we can estimate an improvement upper bound on the system in understanding how well could we do if we were able to implement all the proposed fixes in this system. And finally, differently from what system designers thought at the beginning of this study, the fixes that were applied to the visual detector were not the most promising ones, and they were actually manifesting non-monotonic error propagation due to complex component entanglement. Here is one example from our studies which showed non-monotonic error propagation. The original caption of this image was a teddy bear sitting on top of a computer. And here we can see that the word computer is in the list. People could remove this word from the list, and they could also improve the confidence scores because now they were sure that these words are actually in the image and they should be mentioned in the caption. And the caption, after applying this fix, becomes a person wearing glasses and holding a teddy bear sitting on top of a keyboard, which is obviously worse than the original output. Now, when we went back to debug and see what was actually going wrong, what happened is that the language model has statistically injected the word person into the sentence because it had a higher belief on people wearing glasses rather than teddy bears wearing glasses, which is the reason why the word person appears there and why the non-monotonic error propagation happens. And this is what we were able to detect via our methodology. So far I've mostly talked about individual fixes in each of the components. However, there are many alternative use cases for this type of methodology. One could, for example, be component prototyping. Say you have envisioned this system which needs to make use of a certain component. However, this component is too expensive to develop at the moment or probably impossible with the current tools. And you could try to prototype this via the human input and see how well would your system do if it had such a component. Another idea would be to experiment with architectural changes. So far, we have been focused mostly on applying fixes that strictly follow the system architecture that was given to us by the designers. However, one could, for example, see whether splitting one of the components in two may give you not only a better modular design, but also a better quality. And finally, since there is usually, mostly often, a gap between the fixes that one could generate with crowdsourcing and humans, and the fixes that system developers can implement. It would also be interesting to actually introduce noise in the human fixes, or, for example, partially apply them, so that you could see how well would your system do, even if you apply imperfect fixes into the component. For example, for the visual detector, we tested 100% improvement on the component. However, we do not know. Maybe it is not possible to have like the perfect component there, but we want to see what if we improve it only by 50%? How well could we do here? So to conclude, I'd like to spend the last few minutes on a few takeaway points that we got from this work and where we are heading to. So obviously, one very clear takeaway point here is that our job does not end with system development and initial engineering. Complex systems that will solve complex tasks, they will need continuous monitoring, evaluation, improvements, but also adaptations to new domains that are yet to come. And in order to do so, we need generalizable frameworks that can expand over a set of systems and not only a single system. Now, it is also interesting to think about what are the kind of tools that these frameworks need to provide. So far, we have been thinking about machine learning as a machinery that transforms label data into models, into predictions, and maybe even decisions. Now, it is, of course, clear that together with these decisions, we also get mistakes or decisions with unreliable confidence or strong biases that are encoded in the model, or non-ethical output, or barely transparent decision-making. Now, as we integrate these models into whole systems, all these issues that I just mentioned on biases and ethical issues, they can get interleaved together in the same way that mistakes can get propagated into a system architecture. So in our work, we say the errors in a system architecture that can get propagated, suppressed, or transferred from one component to the other. But one could say the same thing about biases and ethical issues. And one could also argue that these problems are equally important to debug and troubleshoot. Now, in our work, we found the human input and intervention as valuable not only for generating supervision data, but also for making more fine-grained interventions in understanding errors. And at this point, it is also important to think if we want to integrate people into troubleshooting these frameworks, we need to think about the different roles that people can have in such frameworks, like not only as crowdsourcing workers, but also as end users and system designers. For instance, in a crowdsourcing perspective, in order to have good frameworks, we need to have reusable tasks, but also clear user interfaces and training for the workers. From an end user's perspective, such frameworks should provide the possibility for end users to collaborate with the system, to give feedback to the system, but also adjust the system according to their needs. For instance, a user could adjust the system by giving new training personal data to make the system better, but also maybe by also flagging mistakes and mispredictions and giving this kind of feedback. And finally, from a system designer's perspective, such frameworks could have better visualization and domain analysis tools in order to understand better and deeper the system. For instance, for the image captioning app that we have considered so far, we want to understand what are the different types of errors that the system makes and what different types of fixes are more applicable to different errors. And as a final point, I would like to say that side by side with troubleshooting, integrative testing tools are also as important for this framework. People have done a lot in software engineering for having good testing tools, and one could also think about what can we reuse from these frameworks, but also what needs to be adjusted for software that relies on artificial intelligence. Yeah, so these are all ideas that are worth exploring in the future, and I'm also eager to learn more from people in this room on what are their real-world problems when they actually deploy these applications in real settings. And I'm excited to learn about the Psi framework that goes into this path. Yeah, thank you.
Questions?
Hi, thanks. The computational linguists used to say that the reason you need grammar was so you could say things that are surprising. You know, the great white shark was eaten by the baby. Or the Final Jeopardy failure where it did Toronto as a U.S. city because just statistically, et cetera. And I'm wondering which types of errors that you're going after are sort of amenable to tuning the system and that versus which ones are sort of a flavor of a failure mode of the nature of how you think about generating captions. And whether you worry about that distinction or how you think about that there are errors that you should go after and errors that maybe you should not go after.
Yeah. So the errors that you should go after also depend on the domain where this system is supposed to work on. This system, when it was first built, the main motivation was to generate captions for people that have visual challenges. And the perfect caption would be the caption that generates a well-descriptive sentence for the users. And this is also the way how we test it and we try to troubleshoot the system. So we wanted to have descriptive captions that had enough information. Now, of course, if you readjust the system to a different domain that needs to understand different things, or for example, needs to output funny captions or creative captions or artistic ones, then of course you need to tell this to the end users that are doing the evaluation and to provide the evaluation criteria. But it is also true that the evaluation criteria has to readjust with the new domain, and maybe also the fixes have to be readjusted to the new domain. Right? Yeah.
One more?
In the last part, you mentioned dealing with ethics and things like that. Do you think your approach will scale to these issues? Because to me, it sounds like involves more difficult problems. Like, can you define ethical or non-ethical outputs, objectively? Maybe you can resort to crowdsourcing, but the criteria may be different from people to people, person to person, or and also you cannot decompose the definition of ethical into functional components. Yeah. At least now. So I don't know how you can, track down the source of problem.
Yeah. Yeah. So I suspect that the problem with biases and ethics has more entanglement than the usual errors. So it might be difficult to track down from which component it comes from. However, what we have seen from the image captioning system is that there are cases when you can actually track this down. We had these examples of a little girl with a red umbrella, and whatever you give to the system will give you as an output a little girl with a pink umbrella. The umbrella was red. The word that was detected from the visual detector was red. And maybe sometimes it had other colors with a very low confidence score. But it was very clear that this was a bias that was generated from the language model because the data that was collected to train this model was also biased. But I think it is worth exploring in seeing how do these ethical issues get entangled together. and whether we actually need a separate component for blocking all these issues, or whether we should have one sub-module in each component that makes the component aware of all this. Right.
Great. Thank you, Bessa. Okay, our final talk for the session is from Dan Bohus. Dan is actually just celebrating 10 years at Microsoft Research. So congratulations, Dan. In that time, he's worked on a ton of physically situated language interactive systems, from directions robots to virtual assistants. And today he's going to be talking about a new platform to hopefully make that work and all of our work a lot easier. So,
thanks a lot, Sean. You guys hear me okay? Yeah, so I guess I'm standing between you guys and lunch. I'll try to keep this short and sweet. I will not be talking directly about research today. I will be talking about a platform for enabling research. I think we're at a time where, over the last years, we've seen a lot of fast-paced advances on core perceptual AI tasks with deep learning, vision, speech, language. But I think it's still the case that when you try to put together multiple AI technologies and construct systems that actually are deployed in the world and that act in the real world, it gets challenging. It's expensive, it's time-consuming, it's error-prone. I think everyone that has built this system knows it. Everyone that hasn't probably underestimates the problems. And so what I want to talk to you about today is an effort that I've been involved with in the last couple of years on developing a platform that hopefully makes this all a little bit, just a tad, a little bit easier, and lowers the barrier to entry, allowing more people to sort of tackle these kinds of problems at the intersection of different AI technologies. Now, to set it all in context, I'm going to start from my own personal research interests, which are in physically situated language. The questions that drive me are, how do we get machines to understand how people interact with each other in physical space with language? Now, when you say language interaction, the mind immediately goes to things like speech recognition. And that's a large part of it, but language is much more than that. It's a very sort of fine-tuned, richly coordinated, mixed initiative, multimodal process. We do a lot with nonverbal behaviors, with gaze, with pointing, with head nods, body pose. All of these play a role. As a simple example of the kind of problem I look at, consider what it would take for a robot to inject itself in a conversation with 3 other people. Well, it needs to know not only what is being said, but who is saying it, who are they saying it to, is this person about to finish talking, and when they're finished, are they going to release the floor? Who do they expect that will talk next? Will someone start talking in the next 300 milliseconds, and so on. Now, clearly, solving these kinds of problems requires bringing to bear many different kinds of AI technologies. You have to do head pose tracking and speech recognition and voice activity detection and sound source localization and integrate all these things together, and that work is hard. Over the years, we built a variety of systems in this space, from things like avatars that try to look through cameras and interact with people and do multi-party turn-taking in the open world, to human-robot interaction scenario. Like Sean mentioned, we have these direction-giving robots that try to synchronize pointing with speech as they interact with people and give directions inside the building. Most recently, we've started looking at what does the mobile dimension add into this equation. What if you have a mobile robot? How can you make that more social as it traverses the environment? So we're looking at a number of questions in that area more recently. I'm going to put a shameless plug in here for a demo we have of this little guy. It's still early days, but we have it in the other room roaming around. Go have a look. So that's the latest platform that we're working on. But really, I'm not here to talk about these guys. I think the argument I'm making is that whether you're in this space of multimodal kind of situated language, or in fact, in any domain that brings together many different technologies, especially if you're dealing with sensory data and with low latency timing constraints, it's challenging. And so what we set out, the challenges to a large degree stem just from the complexity of these systems. Like, they have many different components integrated in them. But I would argue that it's more than just complexity. We are missing a bunch of fundamental primitives, I think, in our programming languages. it still surprises me that time, the very notion of time, is not baked in our programming languages. Same with uncertainty. So every time we go and construct these systems, we kind of have to go back and reinvent the wheel. And being in research, usually we don't do a spectacularly good job of it. Now, building the systems is not even half the story. I would say maybe a quarter of the story. I think 3/4 of the story has to do with debugging and understanding why they don't work, because they won't work. And so trying to debug these kind of complex pipelines where everything happens asynchronously, for anyone that has done it, they know how painful it can be. And again, it's a lack of tools, I think, that we have in this space. And then to put the cherry on top of everything, Bessa already talked about machine learning. A lot of the components in these systems are machine learned, and they interact with each other, and errors propagate in funny ways, and so on. And so driven by basically our experience and lessons we've learned over the year developing these systems, and from experience other people in our group have from robotics, we said to ourselves, well, why don't we take a stab at this and try to construct a platform that will simplify at least some of these tasks, and enable other people to do research faster. And so we're building this platform for situated intelligence. We're referring to it as PSI for PSI. But basically there's three big components to this framework that brought together kind of provide the value and enable faster development and research. The first part is a set of basic primitives and a programming model for parallel coordinated computation that we refer to as the runtime. Secondly, there's a set of tools that are heavily focused on visualization, debugging, and enabling a very fast machine learning loop that allows people to sort of develop their models and inject them into running systems. And thirdly, we're constructing a store, if you want, of AI technologies, a repository of AI technologies that can plug and play relatively easily with each other, and that hopefully help developers stay at the high level and push the boundaries from there on. So what I want to do briefly in the remaining time is just give you guys a couple of highlights in each of these areas. Yeah, so I'll start with the runtime. The runtime, as I said, provides a set of basic primitives and a programming model for parallel coordinated computation. How do we write applications? Well, I'll go back to the question, to the problem that I put before of how does a robot inject itself in this conversation. The first problem it has to solve is knowing who is talking, and clearly that's a multimodal problem. You need to connect multiple components. Using the PSI runtime, basically you just get to connect components to each other. It's what you would think of it. You know, you have a camera, a face tracker, a microphone array, a sound source localizer, and you bring them together. Nothing special so far. And these components communicate with streams that pass messages to each other, right? So it's sort of a very normal kind of graph architecture. What makes the streaming infrastructure in PSI interesting, though, in contrast to other streaming infrastructures, is that the streams are time aware. So at the moment a message is created, when we encounter it in the world, the moment the time frame, the frame is acquired by the video camera, we timestamp it, and as it travels through the component chain, the runtime is aware of the latency, and the components are aware of the latency by virtue of that. So this helps solve a couple of problems. One problem that often you run into these systems is synchronization. The message that came through the camera through face tracking maybe took 430 milliseconds to get here, whereas this other guy is just 110 milliseconds delayed with respect to the world. And so we're providing a time algebra and the right synchronization primitive so that the developers of the systems don't have to think through all of that and solve that problem. We're managing a lot of that automatically. The second aspect that this time awareness kind of enables is a very performant type of scheduling. So the components in these systems all execute in parallel and asynchronously. They're isolated from each other, and we maintain isolation. But we have a scheduler that, because it's aware of all the time and all the latencies, can retain really good scale-up properties. Like if I give you more computational power, this thing will leverage it and will use it. But if the computation power, for whatever reason, goes down, if there's pressure on it, it will degrade gracefully. And so there's all this work that we've done on the lower level to make this sure that these systems run smooth and like butter, and the scheduling is done properly. Finally, the last bit I want to say about the runtime is that all the data that travels through these streams can be automatically persisted no matter what type it is. So you get a uniform logging infrastructure where you don't have to worry about logging in your application. Everything can be persisted. And this is fundamental when you do work with machine learning, data-driven models. It's another step that we're removing sort of from the friction that a developer typically encounters. And with the data, I'll switch gears and talk a little bit about the tools. As I said, the tools are geared a lot on debugging and visualization and machine learning. Visualization is fundamental. What I have here is a video running of someone interacting with the visualization environment that we have. But basically, anytime you want to debug these systems, because of the complexity of the things involved, you really need, you cannot set breakpoints. You really need to go and visualize and be able to see your data. You can inspect all the streams that your application has and construct different kinds of visualization. The visualizers are composable. You can overlay, that's a visualizer for a stream of images, overlaid with a visualizer for faces. We have an audio signal here, overlaid with a voice activity detector, and then with speech recognition results. All the way to basically constructing more interesting kind of visualizers. This shows latency of messages, like of partial results from the recognizer, where the message was generated here, but by the time the results came back to the cloud, I was actually here, all the way to 3D understanding of basically the scene that the system assembles as it interacts with people. And so we've put a fair amount of effort into this, and it continues. We're further developing these visualization tools as they play a fundamental role. The visualizer system is set up, distributed. It can run live, so you have an application running live somewhere. You can connect to it, and you can see what's going on in a live running application, not only on offline data, and so on. You can navigate through it, all what you would expect. Another really important capability, and this is again because of the runtime persistent streams with all the timing information, is that you can replay this data and experiment. So once I've captured a session with my camera and microphone, I can just start replaying the same data. And we have, because time is under control, we virtualize time, we have the capability to run, let's say, replay just at the speed that the camera was going, like it was happening in the real world, or go as fast as you can as long as no one else down the pipeline drops, and things like that. So there's a lot of infrastructure allowing people to experiment over data and tune a component and then look how would that have looked like. And that, again, helps with this entire debugging and maintenance and experimentation process. And finally, we are putting a lot of effort into streamlining machine learning. We're not into developing new machine learning algorithms. We leave that to other people. But what we're looking at is creating a very fast loop, because oftentimes the work in machine learning ends up being about writing Python scripts or Perl scripts to process some data and move it from one environment to another. We're trying to keep something that's very tight and that gets you all the way really quickly to integrating and running the model back into your system, so that more models actually see the life of day in real-time applications, don't just sit somewhere in MATLAB scripts. And so we're developing on that front as well. The third bit I was going to talk briefly about is the set of components. And here it's what you would imagine. We're wrapping a lot of existing technologies, from sensing technologies to vision, speech, various kinds of human perception technology. There's a long laundry list. We're also being careful to bridge and interop with other existing ecosystems. We have, for instance, bridges to ROS for people that are doing robotics, bridges to OpenCV, and we're constructing more such integrations where we're bridging to other existing ecosystems. We want everything to kind of play nicely and sort of enable more research. The final bit I will say here is that separately, given my personal interest in language and this kind of physically situated interactions, we're building a toolkit which you can think of it as a set of Psi components that are geared towards enabling or constructing this kind of language interactive systems that reason sort of about higher level constructs like identity, attention, interruptibility, and all these things that you need to reason about when you're interacting with people in the world. So I think I'm going to close on this. This is a platform that we're planning to release, and so we're inviting collaboration. Get in touch with us if you think you might be interested. I will also say we will run a small kind of, we can go in more details with questions and all the way to the code. We'll run a short tutorial at 1:15 and at 2:15 in the lesson room in parallel. It's set up in parallel with the technology showcase, with the demos, but we're doing 2 consecutive sessions, one starting at 1:15, one at 2:15, so you can attend any of those and then see the demo still in the other part But hopefully this is something that people will find useful. We certainly know it's kind of simplified our own lives. And I'll stop here and take questions.
So thanks. This looks super useful to me. One of the common kinds of problems I run into working with real-time systems is when you have a component that's making a decision, and but it's making the decision based on kind of stale information. Mm-hmm. So you have a downstream component like a generator that's generating something in real time, and you're kind of looking at it and saying, okay, something went wrong. I'm not quite sure what went wrong. You go look at your module and it looks like it's working correctly, but if you really drill in, you figure out that the information that it needed to have to make the correct decision was in the pipeline, but it hadn't reached the module yet and that sort of thing. So I'm wondering, like, do you have support for kind of navigating kind of what was the information that was available at the moment this decision was made?
Yeah, so we're building exactly. So I'm very familiar with the kinds of problem here. I completely sympathize. Yeah, so a lot of the runtime is around this time algebra that basically provides you visibility, first of all, into that. Then on top of that, we're constructing the right kind of visualization tools. Now, the visualization tools I showed you here mostly let you look at the data. At the same time, we have other kinds of tools that let you dump a pipeline as a graph and see basically the messages that were received when. So you kind of have full visibility because everything is timestamped. Now, of course, I think there's more. There's more kind of tools that we need to build. Layers in here, to allow you to kind of fastly narrow down on something and not have to search for it. But in the long run, I mean, I'm really envisioning this as sort of, if you're almost like integrated as a development environment, like with Visual Studio, where you can maybe activate historical debugging based on something and go back in time and see what exactly happened at that point. And yeah. Those are the problems we're trying to solve.
Thank you. So presumably it's, I mean, you've got a data flow system here, and presumably there's ways that I can set up a barrier where I can actually wait for things that
yes.
are... Okay. Secondly, it seems, have you developed a way to encapsulate existing bits of code that can plug into this runtime?
Yeah, so no, so what we're doing right now actually for the component development is we're shrink wrapping a lot of existing technologies, and the wrapping of the technologies into this fabric is actually pretty straightforward, and to the point where we're thinking, for certain kinds of classes of problems we might be able to do it automatically. But the wrapping is mostly consisting of, hey, say you have a parser, takes in a string, gives me a parse tree. I mostly have to shrink wrap a component that says, now I'm going to take a stream of string and I'm going to put out a stream of parse tree, where stream is a primitive from our library. So we do, the effort to shrink wrap things is relatively lightweight. And yeah, the hope is that we can take a lot of existing technologies and kind of get them to participate in this ecosystem. There's one question here.
One more. Right at the front.
Right here at the front. Right here at the front. Sorry. Oh, yeah.
It looks like a very useful system. You mentioned the bridge to ROS and OpenCV. I think these are very important practically. To what extent can they be accommodated into the system? Like in a way, like you mentioned, the shrink wrapped, or so that you can use all these ROS components in a modules. Then you can keep track of the timed streams.
So what we're actually doing with ROS, for instance, it's an actual bridge. So it's a real bridge. So you can have an entire ROS system running, streaming to another size system, and the two communicate with each other. Actually, the demo of the robot that I showed, the mobile robot that I showed, that's going to be demonstrated. The way it's implemented is got, I think, a ROS system running for some of the navigation bits that runs on a Linux machine, coupled with a bunch of Windows SI components running the system for interaction and for interacting with people. So.
Then my question is that when you talk about a componentized system, like you think about it like the different component needs to tolerate the errors from each other when they're communicating with each other. I was wondering, is there any thinking like when you put all these pieces together, is there a way you can do some end-to-end optimization sort of thing to make it perform really in the best way?
Absolutely, absolutely. So I think the time awareness, provides part of the key here. So I'll fork my answers into two different bits that I will say. One, with respect, because we have time awareness, you could imagine, and we've actually worked out through examples where I can run an online learning algorithm that tunes a parameter on one of the component to obey some constraint later in the pipeline. I want to say latency 5 components after my face tracker, I want it to be around 600 milliseconds, but no longer. And I have all the information I need to learn online, basically how to do, and we're planning with the runtime to evolve it in those directions. Now, there's also, when we say errors, there's errors that have to do with time and with messages that get dropped, and that's where the runtime has a lot of visibility. And then there's errors that are semantic, like, for instance, this particular component said the wrong thing. Those we have less visibility into, but we're still hoping to provide a bunch of, information and tools for people to build models to address those challenges. I think what's important is this unified kind of fabric, unified infrastructure that would allow us to study, the kinds of problems that Bessa is talking about, not in a one-by-one fashion, but rather when I have 15 systems implemented on this platform, because at the bottom it's all unified, I can look in a systemic way at what are the characteristics, and I can try to learn something across many different systems as opposed to kind of in this piecewise fashion. Yeah.
Your opening line was exactly right, that it's unbelievable but true that time is not a fundamental primitive to most of these things. Those of us who've worked in labs where time happened, one of the reasons people embraced ROS was at least, even if you weren't using robots, you could connect this stuff together. From a research community perspective, it would be great for in some sense for this to enable some research thinking deeply about how time is best represented for these kinds of systems. Timestamps, we understand a reasonable amount and being able to buffer them so you can get to them, and it's great that it's going to support that. There's this question, of course, of intervals and how that, and by you creating a system like this, it'll allow folks to experiment with exactly that. So the more all I'm trying to do is advocate for you exposing as much of that as possible so we can play with that, because I'm going to guess that pretty soon people will run into limitations on any particular time model that you embed, timestamps or otherwise. And man, it is so critical to us building systems that actually engage out there. So, the more you expose that, the happier we're all going to be for that.
Good. Yes, that is exactly the goal. The goal is to, I want us to, ideally in the long run, I want us to get to almost like understanding more deeply a science of how do we do integration. And time is a big part of it. And, the other big part in that equation where I hope that frameworks like this will help us sort of study is uncertainty. Because uncertainty propagation in these systems and dealing with uncertainty is another thing that has the same kind of challenges around it.
Okay, I think it's about time for lunch. Thank you again, Dan. Thank you, Bessa. Thank you, LP. Thank you all for coming.